I am the other Norman Cook. The one you know is the famous DJ who goes under the name Fat Boy Slim. I am Fat Boy Bald. I'm here with two previous graduate students and a current graduate student, and we are mad about harmony. Been doing things for about 15 years along these lines. And I'd like to briefly show you what we do for visualization, and we have a poster later that we can get into some details on that. Before I get into the harmony story, I think it's important to mention the interval perception story, which is, I think, well known. Starting with a curve like this, going back to Helmholtz, but Plomp and Levelt in the 60s have used this curve to explain interval perception, two-tone consonance and dissonance. Now, as you probably know, perception of intervals is more complex than this. This is the model. It works all right for some purposes, but behavioral data will tend to look like this, a little bit more complex. And what Plomp and Levelt, and in fact Helmholtz and others have talked about, is that the behavioral data can be explained rather well if you consider upper partials. So you bring in the first set of the first higher harmonic, the next higher harmonic, and gradually the curve gets more complex. The model is the yellow one at the bottom there, but up to the sixth upper partial, then you get this green line, which matches fairly well with behavioral data. David Huron would say it's not good enough. There's still work to do in interval perception itself, but more or less the behavioral data corresponds with the model if you bring in the question of upper partials. So this is also turns out to be important for what we do. We have a very simple model that without the upper partials doesn't really make sense, but if you bring in the upper partials, then we get some interesting effects. Oh yeah, one other point here is that just explaining why scales tend to emphasize the octave and the perfect fifth and the perfect fourth is also explained using the upper partial story. In any case, as soon as you jump to three-tone effects, then things get more complex. And what the only innovation we've added here is what we call the triadic grid. So instead of having just one dimension for the explaining interval consonance and dissonance, we have a two-dimensional grid. And it's the structure here that I just want to point out briefly is on the y-axis here we have the size of the lower interval of a three-tone triad, and on the x-axis we have the upper interval in semitone intervals for a triad. So on that kind of grid you get the placement of the major minor chords as 4, 3 is the major triad in root position, 3 and 4 across is the minor triad in root position, and so on. So this is just the structural grid onto which we then map various psychoacoustic properties. So understanding the grid is important as a starting point. Not too complex, but this is our innovation. So to talk about the dissonance, consonance and dissonance of a triad, we use the grid, and we get a picture of something like this, where the red in the corner here is when either of the intervals in the triad is small, 1 or 2 semitones, and you get this peak of maximal dissonance in that corner with these yellow stripes where either of the intervals is small. Meanwhile, you have this huge blue area which is more or less consonant, right? But this is with only using the fundamental frequency, no upper partials yet, so the doesn't explain a whole lot. So we bring in some upper partials. Here's the first set of upper partials, and the map gets a little bit more complex. Again, red and yellow are areas of relative dissonance, and the blue is the valley of consonance. Now what's obvious here is that the major minor triads are the M, large and small m, and other chords are in the valley of consonance. That makes sense. But what doesn't really make sense, what is a little bit problematical, is that even if you add lots of upper partials, so this is up to the 6 sets of harmonics, you have the major and minor chords there and these stripes of relative dissonance. No surprise there. But what is a problem is the location not merely of the major minor chords, but here designated as D, S, and A, the diminished, suspended, and augmented chords are also in this valley of consonants. Now that's not consistent with the way we hear triads. There is something unusual about these chords that the major minor chords differ from the way we perceive major minor chords. So it's this effect that we want to explain. Going back in the literature, we have found probably the first expression of the idea that we have pursued, and it's from Vincenzo Galilei. That's the astronomer's father, who was a music theorist. And in 1588, he was fighting with the authorities. And what he said in a pamphlet he produced was, two successive consonances of the same size do not produce a consonance. And this is both melodically and harmonically played as a chord. This is what the diminished, the augmented, and the suspended chords are, or certain versions of those. So you have 3 semitones followed by another 3 semitones, and of course all the chromatic scales have the same quality. It's something unusual, something tense, ambiguous about equi-sized intervals used either harmonically or melodically. Now this is something that Leonard Meyer also discusses a few centuries later in his book Music and Emotion, and he calls this intervallic equidistance. So you have 3 semitones and another 3 semitones, or 4 semitones and another 4 semitones, again played melodically or harmonically. You get this sense of unresolvedness, and we call this harmonic tension. Don't think those sounds will come out, but so starting with Vincenzo's insight, we've turned this into a psychophysical model. And the model is very simple. It's this curve at the bottom here. It's calculated by simply finding the difference between the 2 intervals in semitone units. So you have 0 difference, 3 minus 3, 4 minus 4, 5 minus 5, 7 minus 7, etc. You get a maximum of tension. And if you have a difference, 4 and 3, the major chord, 3 and 4, the minor chord, etc., then you slip off of the tension curve here into a valley of lack of tension or resolvedness. So that works nicely for the diminished, the augmented chord, the suspended chord in those inversions, and for these major minor chords. But what about other chords, and how well does this generalize is the big issue. So first of all, again, back to the triadic grid. If you plot this on the grid, you see this diagonal. This is where there's maximal tension, and the blue areas is where there's not much tension. But you'll see there are various suspended, diminished chords that are off of the diagonal. So what I want to show you, what was convincing for us a few years ago, is when we plotted this with the first set of upper partials, you get these other oblique lines, and sure enough, all of the suspended, diminished, and augmented chords fall on these oblique lines. These are areas where there's a little bit more tension calculated with that kind of tension curve than elsewhere. And just off of these tension peaks are the white letters here, the major minor chords. So again, you can keep adding upper partials. The topology of the map gets more and more complex, but as you see on the right there, it's these peaks of orange and red is where you'll find all of the tension chords, augmented, diminished, and suspended chords. So this was our first attempt at psychophysical modeling. But from there, we said, wait a minute, there's two things going on here. There's the interval story, that's dissonance, consonance, and there's also this 3-tone effect, which is what Vincenzo was talking about. It is a 3-tone acoustical effect from which you can calculate tension. So what we do is we add these together to get a total instability score. And that's mapped here. So again, the diagonal is tension, and the vertical yellow stripes are the dissonance curves. Again, this is the fundamental frequency only effect. Doesn't explain a whole lot. But again, if you add upper partials, then you get this very nice map that shows that the major and minor chords fall just off of these peaks of instability, and they're in these valleys of stability. So to focus in on that, yeah, and again, adding upper partials doesn't change the whole story, makes it a little bit more complex. Focusing in on that lower left-hand corner here, you'll see that these little valleys of these pockets of relative stability is where there's less tension and less dissonance. So this was for us our first indication that maybe we're onto something, because this is a purely acoustical calculation we're making, or it's entirely computational. There's no music theory that comes into this to get these little locations of major and minor chords. So this is what our poster is about. We have this software that is connected to a MIDI keyboard. You can play music real time, and the cursor bounces around depending on what chord you've hit to indicate the visual analog of what you're hearing. So this is the stability instability story. But there's one other story that I just want to mention briefly. Oh yeah, this is software that's available. Source code's available. If you find this at all interesting, we'd love to do some collaboration. One other story related to this is what we call the modality curve, and this is calculation of how major or how minor a three-tone combination is. Again, this is quite distinct from music theory, harmony theory. This is a purely acoustical calculation. Again, we use the difference in the size of the intervals for the calculation. So 3 and 4 will give you a difference of 1, a difference of -1. That will be the minor trough there, a minorness score of -1, and 4 and 3 or 5 and 4 will give you a peak of majorness in the same way. So again, to put this onto the triadic grid, fundamental frequency only is not very interesting. You get this kind of stripe here with a major peak and a minor trough, and a few major and minor chords that are in the plane that's neither major or minor, and that's not correct in terms of what we know about the sounds of those major and minor chords. But if you bring in the first upper partial, and other upper partials is fine, but simply with the first upper partial, you get this very nice little map. This is again the lower left-hand corner, where you see that there's a 3 peaks of majorness calculated with that modality curve, and 3 troughs or deep wells within the yellow troughs of minorness. Right. Yeah. And again, bringing in the upper partials it makes the whole thing more complex. But you find throughout the entire triadic grid, this is 1 octave by another octave. You can expand that as large as you want, and you'll get major, minor peaks and troughs at the right places. I'd like to just jump ahead here to the conclusions. Our main point simply is that this is acoustics. This is not the major and minor distinction. The resolved chords versus unresolved chords is not a cultural tradition that's been inherited from lute players from the Italian Renaissance. This is acoustical. It's computational. So that both the resolved, unresolved issue and the major-minor issue has a fundamental acoustical character. The point we want to make here in terms of cognitive psychology is the interval consonance-dissonance story is about 2-tone combinations plus their upper partials, whereas Vincenzo's story is a 3-tone combination, again, plus all the upper partials, but it's fundamentally 3-tone psychology versus 2-tone psychology. Thank you very much.
Thank you very much. Do we have any questions?
Yes, sir. Yeah.
Sorry, go ahead.
I have a question. Three-tone zones produce 3 intervals, basically.
Right.
So when you have 2 equal intervals,
Yeah, well, you could,
So what if you would you include this in the cost?
yeah, it is in fact included in the computations. For location on the grid, we just look at the two intervals, so it's a 3, 4, or 5, 5, or whatever.
Yes, yes.
That's the location. But the computation of total dissonance or tension or modality, we use all combinations. So you have your lower interval, the upper interval, and this other interval are in fact included in the computations of the total tension.
And it still does not explain why this, and you still need this other curve, this bell-shaped curve in order to explain the...
Yeah, dissonance,
Okay.
interval dissonance alone will not do it. Yes, sir.
I probably already know the answer, but how does this relate to Hindemith's kind of chart of the relative dissonances and stuff like that? I imagine it concords pretty well.
I've looked at that. I don't have a one-sentence answer to that, how it relates. It relates to music theory, I would say,
Okay.
and his is certainly that. We'll talk later, I think. Yes, sir.
Just if you have a 4-tone chord, so say dominant 7th, where does that start to fall on the chart? Because then you have 2 equal intervals.
All right. It makes no difference how many tones you have to make these kind of calculations. And what I skipped over here, the dominant 7th chords are major related, and they are peaks on the topology map, and the minor 7th are also are wells, troughs on the map, so that the equal intervals within those chords, within the dominant 7th, will bring the peak down a bit, but does not eliminate it.
Okay.
I think we have one other question over here. Yeah.
I find it a provocative position you presented at the CogMIR conference by saying that all the information is in an acoustic signal, and music theory doesn't matter, and cognition as well.
Right?
So, I appreciate that. But could you say where the boundaries, where would you read cognition? Or do you think cognition is also a mere result of characteristics, acoustic structure?
Yeah, I think this is a truly human characteristic. Cognitive characteristic is dealing with 3 kinds of information at the same time. So it's 3-tone perception is something that I consider purely a cognitive event that we human beings can do. And as far as I know, animals cannot hear the major-minor distinction. The bird studies that have been done seem not to be able to make that distinction that we so easily do. So I think it's 3-tone cognition is what we're talking about.